So there are many, many different ways that one can interpret the definite integral in a variety of contexts. We're going to look at 3 in this class. If you take Calculus 2, you will learn many, many more. You'll learn ways that relate to, say, economics, present value in economics, future value in economics. You'll learn things related to probability, to densities, all sorts of different things, work from physics. Definite integrals are incredibly useful. The first one that we're going to look at is area. So we've already seen this to find basic questions of area. So we'd like to do something a little bit more complicated, finding the area between two curves. So this is a case where the area is always positive. Whether these curves are below the x-axis or above the x-axis, the area between them is considered a positive area. So what do we need to do in order to figure out, before we can write our integral here? There's 2 things we need to do. First, we need to figure out where the curves actually intersect. This is a line and this is a parabola. So if you imagine they could intersect in 2 places, which is what is going to happen in this case, or in 1 place, or not at all. So how do you find out where 2 curves intersect? This is an algebra question. And I hope you're answering to yourself that we set them equal to each other. So we want to solve x squared minus 4x plus 5 equals 4x minus 7. This is a quadratic equation. We usually like to get quadratic equations equal to 0. So if we bring everything to the left side, we get x squared minus 8x plus 12 equals 0. And of course, you can always resort to the quadratic equation, but in some cases, you get lucky, and it'll factor nicely. So we're looking for 2 numbers that multiply together to give us positive 12, add together to give us negative 8. I think x minus 2, x minus 6 will work nicely. So that means x equals 2 or x equals 6. So those are the places where the curves cross. What we don't know yet is which curve is higher up. You might be able to reason it out based on just generally what a line and a parabola opening upward would look like. But in general, how do we find out which curve is higher? And in particular, we care about which is higher on the interval 2 to 6. We can just pick a number between 2 and 6 and plug it in. So plug in x equals 4. When I plug it into this, I'm going to get 4 times 4 minus 7. And when I plug it into this one, I'm going to get 4 squared minus 4 times 4 plus 5. So this is just 5, whereas this is 9, I think. So this is higher. So this tells us that the line is the higher of the 2 graphs between their intersection points of x equals 2 and x equals 6. So we'll illustrate this with a picture now. You did not need to know this picture in order to do this problem up to this point or at all. So they cross at 2 and 6, and in between 2 and 6, the line is the higher of the 2. So if we want to compute the integral, we want to compute this area here. That's the area we want to find. We can do that by finding the area under the line. That would be this entire trapezoidal shape, and then subtract off the area under the parabola. So the area under the higher curve minus the area under the smaller curve. And you could write this as 2 separate integrals, but typically people just write it all together as one integral. So then the area will be the integral between 2 and 6 of the higher curve, which is 4x minus 7, minus the smaller curve, shorter curve, x squared minus 4x plus 5. Right? Because if we broke this up into 2 separate integrals, which we're allowed to do by one of our properties of integration, definite integrals, this is the area under the line, and then this, with an integral sign, is the area under the parabola, and therefore when you subtract, we'll get the shaded area just like we're supposed to get. We can simplify this a little bit here. So if we subtract, we'll get a negative x squared. We'll get 4x minus negative 4x. That's plus 8x. And then negative 7 minus 5 is negative 12. And this equation should look familiar, right? This function. It is the same as this, except multiplied by a negative 1. And now we just use our integral techniques here. So the integral of negative x squared is negative x cubed over 3. This is going to become what? 8x squared over 2, but 8 over 2 is just 4, so 4x squared, minus 12x. And I think I've mentioned a few times how mathematicians try to be as lazy as possible and avoid writing symbols. So often here, instead of writing a vertical bar here, since we've already got a vertical line, they'll just write the 2 and the 6 right there. It's true. So this means that we're going to plug in the 6 first and then plug in the 2. So we're using the fundamental theorem of calculus here. So negative 6 cubed over 3, 4 times 6 squared, minus 12 times 6. And then we plug in the 2, minus 2 cubed over 3, 4 times 2 squared, minus 12 times 2. And we know we're going to get a positive answer because we're taking something bigger minus something smaller. And the same would have been true whether this was below the x-axis. So imagine that the x-axis were somewhere up here, and both these curves, the curves were intersecting underneath the x-axis. We'd still be taking the bigger number minus the smaller number, meaning that this quantity would still be a positive quantity in there. We would still get a positive area. Areas are positive whether they're, when we're talking about the area between a curve, whether it's above the x-axis, below the x-axis, doesn't matter. The area between curves always has to be positive. We won't bore you with the details of working out all of those numbers there. I did it on my own, and I got a positive number, as I was expecting, 32/3. So that's how many units of area we've got between those two curves. We have an applet that lets you explore area between curves by drawing some Riemann sums. And we have a check your understanding, so you can practice one of these on your own.